Thanks everyone for coming. So today I have the pleasure of introducing Dr. Soizic Terrien. Dr. Terrien is joining us from the University of Longterm in France, where she's a CNRS research fellow at the Laboratory of Acoustics. Dr. Terrien holds a PhD in acoustics from Aix-Marseille University in France, and that's where she studied the nonlinear dynamics of musical instruments, and in particular in models that can be used in expressed in terms of delay differential equations. So she has several contributions in this field, for example, on the dynamics of flute-like instruments. And after her PhD, Soizic joined the University of Auckland for postdoc, where she was working at the Department of Mathematics and Doddswell Center for Photonics and Quantum Technologies, and working with Bernd Kroskopf and Neil Broderick. And that's where she was working on dynamics of excitable lasers, again with delay differential equations. So she knows a lot about the delay differential equations, and she's going to tell us today about her work with excitable lasers. So the floor is yours.
Okay, thank you very much for the introduction, and thank you very much for inviting me for the seminar. It's really a pleasure to talk today. So I will talk about equidistant and non-equidistant pulsing patterns in excitable microlaser with delayed feedback. And so this is joint work with Bernd Kroskopf and Neil Broderick from the University of Auckland, and also with Venkata Anirudhpami and Sylvain Barbet from the Center for Nanosciences and Nanotechnologies in Orsay, close to Paris. Okay, let's start with excitability. So it's a very general phenomenon, and actually it corresponds in a system to an all or non pulsed response to an external perturbation that we can also call stimulus. So if you plot here the response of a system, for example, the intensity of a laser with respect to time. So the laser is basically off, so it doesn't emit light, intensity is 0. And if you give a small perturbation, in the one case, which is quite classical, then the intensity will just decrease back to 0, and the laser will come back to its rest state and nothing will happen. But if you give a perturbation with a slightly larger amplitude, which is represented here in blue, if the system is excitable, the system will first release a large pulse and then go back to its rest state. So this excitability phenomenon is encountered in many different systems. For example, in biology with muscle cells, for example, in the cardiac muscle, also in nerve cells. So for example, in neurons, you have different kinds of excitability. And in the physical world, we also find excitability in some lasers, in particular semiconductor lasers, and in chemical reactions. So this excitable response in any excitable system is always followed by what we call a refractory period, and it corresponds to a time period during which no other excitable response can be triggered. So you have kind of this blind window during which you cannot excite a new pulse. And this refractory period is linked to the interplay between different time scales in excitable systems, but I will come back on this a little bit later. So the idea of the work we did here is to couple an excitable system with delayed feedback. So the basic idea behind that is that in the presence of feedback, you can trigger a first excitable pulse in an excitable system by an external stimulus. And as this first excitable pulse will travel in the feedback loop, it will, after a while, after a delay tau, it will be reinjected in the excitable system, which can trigger a new excitable pulse. And so as the process repeats, you can have a periodic pulse train with a period which is related to your delay tau. So basically the pulse, the first excitable pulse regenerates itself after each delay time tau. And so here the setup we study to investigate the effect of feedback on excitable system is an excitable microlaser with delayed optical feedback. So the experimental device was done by Sylvain Barbet and his group in Paris. I will present it again a little bit later. So basically what we have is an excitable laser. So we have here the corresponding phase portrait in the gain of the laser and intensity of the laser plane. It's represented as here. So we have basically this phase portrait with the off state solution, non-lasing solution, so zero intensity. And here the two dots correspond to a case where we don't trigger an excitable response, and the blue dot to the case when we trigger an excitable response of the laser. And so we couple this excitable laser with a feedback loop, which is introduced just by an external distant mirror. So here the delay time is controlled by the distance basically between the excitable laser and the mirror. And the aim is to get auto oscillations, self oscillations from this device. And so the goal of our work here was to investigate the influence of the feedback loop beyond the regular self-pulsing. So investigate a bit more the influence of different parameters, feedback parameters, and time scales parameters. So the experimental setup corresponding to this system is an excitable microlaser with one gain section and one saturable absorber section. And it's optically pumped, which means that we provide energy through an other external laser. And we can provide small perturbation in the form of pulses provided again by an other external laser. So the dynamics of the laser itself without feedback has been quite extensively studied experimentally. So when we increase the pump parameter, which corresponds to providing more energy to the laser. So for the lower values of the pump, we have simply a non-lasing solution. The laser is off. When we increase a little bit, we are in the excitable regime that I described before, and past the lasing threshold, when the non-lasing solution becomes unstable, the laser is able to produce self-pulsations already by itself. But an important limitation of this self-pulsing regime is that it's very sensitive to noise, and the pulsing period is very irregular. So it can be also an advantage of the excitable configuration with feedback, that we can more control the pulsing period more precisely. And so delayed optical feedback is introduced through free space propagation and reflection on a mirror. So in all the results I will present today, for all the results, we are always in the excitable regime when there's no feedback. So if we just switch the feedback off, we are in this excitable regime. And so we consider a mathematical model to study this system. So originally, the solitary laser without feedback can be described by a system of 3 ordinary differential equations, which are known as the Yamada model. So we have an equation for the gain, G, an equation for the absorption, Q, and an equation for the intensity, I. And an important point here is first that A is the pump parameter, so it corresponds to the energy we provide to the device. And another important point is that we have here 2 small parameters, gamma G and gamma Q. And they are small compared to 1, which means that the gain and the absorption variables evolve on slow time scale compared to the intensity. These 2 parameters are related to recombination rate of carriers in the gain and in the absorber. And from a physical point of view, it also means that they are related to a kind of recovery time, slow recovery time after a pulse has been emitted. So this is related to, their values are related to the refractory periods that I talked about a bit before. So this system describes the laser itself. Now we transform it in a system of 3 delay differential equations by introducing a feedback term in the intensity equations, which describes the fact that we reinject a fraction kappa of the intensity, of the output intensity, after delay time tau in the microlaser. And so we introduce 2 new parameters, tau and kappa, which are related to the feedback loop. So overall, we have a system of slow, fast, delay differential equations with 3 different time scales, because gamma G is different from gamma Q. And so what we focus on here is to investigate first the influence of feedback parameters on the dynamics, so kappa and tau, and also the influence of the time scales ratio on the short and long-term pulsing dynamics, so how the ratio between gamma G and gamma Q can change or not the pulsing dynamics. So, okay, in the first part, I will describe the case of a slow gain. So when gamma G is slower than smaller than gamma Q, which means that the gain is very slow. The saturable absorber is a bit faster, but still slow, and the intensity is a fast variable. Then I will present some results when the 2 time scales, gamma G and gamma Q, are in the other configuration. So the gain is faster than the saturable absorber. And then I will talk about some resonance-induced pulsing dynamics, which is related to some phenomenon we will see in the 2 first parts. So in the case of a slow gain, when gamma G is smaller than gamma Q, we can compare experimental results with simulation results. And we represent it here in a pseudo space representation. So what we do is that we take the temporal traces of the intensity, so basically time series of the output intensity of the laser, and we chop it in small segments of length 1 tau, of duration 1 delay tau, and we stack these segments vertically on this representation. So what it means is that the x-axis corresponds to what happens during 1 delay time tau, and the y-axis corresponds to the number of round trips in the feedback loop. And the intensity, the output intensity of the laser is represented by the color scale. So here, for experimental results, we see what happens when we send 1 external perturbation. So the laser is initially off. We send 1 perturbation, which triggers an excitable response. And we see that this single external perturbation results in a train of intensity pulses. So this corresponds to the, let's say naive or basic idea behind the fact of coupling an excitable system and a delayed feedback. So we regenerate an initial pulse in the system, and so we have a regular periodic pulse train in the system. And so what is interesting is that we can do that. We can sustain simultaneously several pulse trains. So if we send 2 external perturbations, then we have 2 coexisting pulse trains in the feedback cavity. It's what we see here. So during one round trip, if we take a horizontal slice, we see that we have 2 intensity pulses. And we can do that with more and more pulses, with more and more external perturbations. For example, here we had 3 coexisting pulses in the feedback cavity. So what is interesting here is that time domain simulations of the model, of the quite simple model, allows to reproduce very accurately the experimentally observed dynamics. So same with 1, 2, or 3 external perturbations. Okay, so if we want to explore a bit more these pulsing dynamics, we can perform a bifurcation analysis of this Yamada model with feedback. And so this is done using a DDE-BIF tool, which is a numerical continuation tool for dedicated to delay differential equations. And so for one fixed value of the feedback delay and one fixed value of the feedback strength, which corresponds at least qualitatively to the experimental configuration, we obtain a phase portrait like this one, which is represented here in the gain intensity plane. So the red dot is the stable non-lasing solution, which means that if we don't give an initial perturbation, we stay off. And we have the coexistence of 6 periodic solutions which are stable together with other non-stable periodic solutions, which I didn't represent here. And so in the right here, we have the time series, intensity time series, corresponding to the 6 stable periodic solutions. So what is interesting here is that they correspond to pulsing patterns with equidistant pulses in the span of 1 delay time tau. And so we have either 1 or 2 equidistant, 3 equidistant, 4 equidistant, 5 equidistant, or 6 equidistant pulses in the feedback cavity. So it's quite a high degree of multi-stability, and it's quite interesting to see that we can observe all these different pulsing patterns for exactly the same parameters depending on the initial conditions, so which corresponds in the experiment to external perturbations we apply to the system. So what we see here is that basically these 6 coexisting stable pulsing periodic solutions have periods close to submultiples of the delay time tau, either tau over 2 to tau over 6. 5 of these 6 solutions are only weakly stable. So the one with the 1 pulse pattern is strongly stable, but the other one are only weakly stable. And interestingly, no stable periodic solution with non-equidistant pulses are observed. So this raises a question, what does this correspond to? Because in the simulation and in the experiment, we can observe pulsing patterns with non-equidistant pulses for quite a long time. This is what we see here for the experiment. So to answer this question, we investigated a bit more what happens in the very long term, both experimentally and in simulation. So here we have experimental results when we trigger 2 non-equidistant pulses, and we represent here what happens during the 200 first round trips in the feedback loop. And we wait for a very long time, and we record 200 other round trips a long time after. So if here after several thousands of round trip. And what we see is that if we look at the distance between 2 consecutive pulses, to the time separation between pulses, that this evolves very slowly, and that this pulsing pattern evolves very slowly towards an equidistant configuration, which corresponds to one of the stable periodic solutions that we find in the bifurcation analysis. This appears a bit more clearly in this figure, where we represent the time that the elapsed time between 2 consecutive pulses, which is represented by the yellow arrow here. And we represent it here with respect to the number of round trips. And what we see is that originally this distance is this time is smaller than half the delay, but very slowly over several hundreds of round trips, it converges towards half the delay time. And this is what we see as well in the simulation of the model. So same, we start from pulsing configuration with 2 non-equidistant pulses in the feedback loop. And we let the simulation run for a very long time for a high number of round trip in the feedback loop. And we see that in the long term, similarly to the experimental configuration, the pulsing pattern converges towards one of the weakly stable periodic solution with 2 equidistant pulses in the feedback loop. So the conclusion of that is that all pulsing regimes are very long transients towards one of the stable pulsing periodic orbit. And because these stable pulsing periodic orbits correspond to equidistant pulsing patterns, this means that in the long term, all pulses become equidistant in the feedback cavity. So there's really a difference between the short-term dynamics and the long-term dynamics. In the short term, we can regenerate virtually any kind of pulsing patterns for a limited number of round trips. But in the long term, we have to remember that we will converge towards one of these stable pulsing solution with regular pulsing patterns. So that's what we can explain from a mathematical point of view, but also from a physical point of view. From a mathematical point of view, this is just a slow convergence towards a weakly stable periodic solution. But from a physical point of view, we can explain why this slow convergence is related to the excitable nature of the original system. So this slow convergence can be explained entirely by the gain and net gain dynamics. So what we call the gain dynamics is just the temporal evolution of the variable g. And the net gain is g minus q minus 1. So it's what we see in the equation of the intensity here. It's the gain seen by the external perturbation when it comes back when it's reinjected into the laser. That's a gain seen by this perturbation. So if we plot here for the configuration, the parameters we considered here, we plot here the gain with respect to time, the absorption with respect to time, and the net gain. And we have to remember that here gamma g and gamma q are small parameters, which means that compared to the intensity, gamma g, the gain g and the absorption q evolve slowly, which means that after a pulse has been triggered, the intensity goes back really quickly to 0, but the gain and the absorber has been depleted, and so it takes time for the gain and the absorption variables to come back to their, let's say, rest state. And it's what we see really clearly here when a pulse is triggered. So there's a refractory period during which there's not enough gain in the system to trigger a new pulse. And here we have first a single pulse in the cavity, and the red line corresponds to the timing at which we introduced a second perturbation. And what we see here is that when we introduce this second perturbation, neither the gain nor the absorption recovered completely. So which means that the gain and the net gain experienced by this new perturbation is slightly smaller than for the other pre-existing pulse. And if we look what happens here for the net gain, g minus q minus 1, we see that indeed the net gain is a bit smaller for this new perturbation compared to the net gain seen by the reinjected first pulse that we see here. And what this means is that the excitable system will take a bit more time to respond to the excitable, to the perturbation. So the delay, the small delay time between a perturbation and the response, the excitable response of the system is related to that value of the net gain, which means that for here, a small defect in the net gain will result in a slightly larger response time of the excitable system for the second perturbation. And so it will result in a larger repetition rate for the second pulse train. And so which means that if we go back to this representation, if the second pulse train has a slightly longer period, repetition period, if you want, it will slowly move away from this first pulse train. And this is how physically we can explain this really slow convergence towards a weakly stable periodic solution until it really stabilizes in a configuration where both pulses experience a same value of the net gain because the interpulse timing is half the delay time. So here we have really a kind of pulse interaction, but the only mechanism for pulse interaction is some memory effect in the microlaser itself, and in particular in its gain section. So that's what happened when gamma G evolve on a slower time scale. The gain, evolves on a slower time scale compared to the absorption. So gamma G is smaller than gamma Q. Now, if we consider the reverse situation where when gamma G is larger than gamma Q, we can have quite different dynamics. And so that's what we explore here. So first, it's physically relevant to consider this configuration of a slower saturable absorber because the pumping process can make the gain faster, which means that even though you design your microlaser so that the gain is slower, by pumping it, you can accelerate a bit the gain dynamics. So what happens in this configuration in simulation and in experiment? So if we consider here the same representation of time traces, except that now the number of round trip is increasing, when we go from top to bottom, we see that when we start from two almost equidistant pulses in the feedback cavity, and we wait for a very long time, again, a very large number of round trips, here the reverse situation occurs, which means that now we end up with two non-equidistant pulses in the feedback cavity. And the same thing happens when we consider three almost equidistant pulses in the first place. We end up, after a very large number of round trips, with three non-equidistant pulses in the feedback cavity. And again, this appears quite clearly here when we represent the interpulse timings with respect to the number of round trips. And in an experiment, actually, we observe similar dynamics. So here we represent only the evolution of the interpulse timing between 0 and 1 delay tau with respect to the number of round trips. So here is what we see for two almost equidistant pulses in the beginning. After a larger number of round trips, the two pulses move away, get closer and closer, from each other. And in the end, we stabilize on a configuration where we have two non-equidistant pulses. And the same thing happens for three pulses in the cavity. So here, conversely to the previous case, in the long term, we have a convergence towards non-equidistant pulsing patterns in the feedback cavity. Oops. So we explore the dynamics using a bifurcation analysis in one parameter, which is the delay tau, for a fixed value of the feedback strength kappa. So here, this bifurcation diagram represents the intensity of the pulsing solution, so the maximum of the pulse, with respect to the delay time tau, up to quite a large value of the delay. So what we see is that when we start from a small value of the delay and we increase it, we encounter successive Hopf bifurcations, which are represented by blue dots. And from this Hopf bifurcation, we have the emergence of periodic pulsing periodic solutions. So they are in red when they are unstable and in blue when they are stable. So from this first Hopf bifurcation here, we have the emergence of a periodic solution with one pulse per round trip. And then we have successive emergence of periodic solution, which corresponds to 2, 3, 4, 5, and etc. Pulses per feedback loop. So except for the one pulse solution, which is always stable here for the span of tau represented, all these periodic solutions have some values of tau for which they are stable and some values of tau for which they are unstable. And what is interesting is to look at how they destabilize when we increase the value of tau. So if we consider the two-pulse solution, which corresponds to equidistant pulses in the feedback loop, it destabilizes here for this value of tau through a period doubling bifurcation. So it's what we see here when we look at the Floquet multipliers at this point. We see that we have a Floquet multiplier which is really close to -1, so which corresponds to a period doubling bifurcation. And if we consider now the solutions with 3, 4, and 5 equidistant pulses in the feedback loop, when we increase tau, they destabilize as well, but in torus bifurcations. And here we represent the Floquet multipliers in the unit circle for this torus bifurcation destabilizing the 3-pulse solution, the torus bifurcation destabilizing the 4-pulses solution, and the one destabilizing the 5-pulses solution. And what we see is that we have always torus bifurcations, but interestingly, they are close to strong resonances, which means that here we have Floquet multipliers crossing the unit circle really close to a third of pi, and which means that we are very close to 1 to 3 resonance. For the 4-pulses solution, we are very close to a 1 to 4 resonance, and for the destabilization of the 5-pulses solution, we are very close to a 1 to 5 resonance. So what is interesting here compared to the previous case is that the periodic solutions with equidistant pulses exist and they are stable on some range of the delay time tau, but when we increase tau, they destabilize at some point, and they destabilize through torus bifurcations, which are very close to 1n resonances, where n is the number of pulses in the feedback cavity. And so this period doubling bifurcation and the 1n resonances, which are close by in the parameter space, generate additional stable periodic solutions. So from the period doubling bifurcation, we can follow the period doubled solution branch, and it is stable here, and it corresponds to 2 non-equidistant pulses solution in the feedback loop. And similarly, close to the torus bifurcations corresponding to the destabilization of the 3, 4, and 5 pulses solution, we have the emergence of pairs of locked periodic solutions. They appear in saddle node bifurcations, and they correspond to boundaries of resonance tongues, which are generated by the strong resonances that we highlighted here. So for the 3 close to the destabilization torus bifurcation corresponding to the 3 pulses solution, we have a saddle node bifurcation where a stable periodic solution and an unstable periodic solution emerge, and these corresponds to 3 non-equidistant pulses in the feedback cavity, and similarly for the 4 and 5 pulses solution here. So now the question is, what do the period doubled and locked solution in resonance tongues look like? So if we consider the case of the period doubling bifurcation of the 2-pulse solution, we can represent the interpulse timing during one period and plot it with respect to tau. So when the equidistant pulses solution is stable, of course, this corresponds to tau over 2. And after the period doubling bifurcation, we see that we have this interpulse timing that evolves with respect to tau, which means that if we look at the time series here, before the period doubling bifurcation, the stable solution corresponds to equidistant pulses in the feedback loop in the span of one delay tau. Just after the period doubling bifurcation, we have an unstable solution with two equidistant pulses in red, but we also have the stable period doubled solution, which corresponds to two non-equidistant pulses with different intensity. And as we increase the value of tau, these two pulses become closer and closer, and their amplitudes become more and more different from each other. So now something similar happens for the case of the three pulses solution. So we have these two periodic solutions emerging through the saddle node bifurcation, which means that we enter the resonance tongue. And so we have one stable periodic solution with three non-equidistant pulses and one periodic solution with three non-equidistant pulses, but so this one is unstable. And we can plot similarly as before the interpulse timings with respect to the delay tau. And as before, we see that when we increase the delay tau, the pulses becomes more and more non-equidistant. They become closer and closer from each other. And they also have different amplitudes. This is what we see here for the stable solution. And for the unstable solution, the pattern is a bit different, but we focus more on the stable solutions that we can observe in an actual experiment. And interestingly here, for the three pulses solution, we see that for the configuration we considered here, we have a small range of coexistence of the non-equidistant pulsing pattern and the three equidistant pulsing patterns, which means that for specific range of the delay time, depending on the initial conditions, when we give three perturbations, which corresponds to three pulses, we can go either to an equidistant pulsing pattern or to a non-equidistant pulsing patterns. So this will depend on the timing of the and amplitude of the initial perturbations. So in both cases here, for the two and the three pulses solutions, the non-equidistant solutions are stable for a wide range of the delay time tau, and the interpulse timings and amplitude can be tuned by the delay. So we can choose what the distance between two consecutive pulses will be depending on the delay time. So we investigate these regions of stability a bit more for the non-equidistant pulsing solutions. And so this corresponds to boundaries of resonance tongues in the tau kappa plane. So now we consider two variable parameters, the feedback delay tau and the feedback strength kappa. So the boundaries of resonance tongues corresponds to the regions of existence of the locked non-equidistant pulses solutions, locked because they are locked on a torus due to the resonance phenomenon. And so here we represent all the periodic solutions that exist for a particular value of kappa and tau. So kappa equal to 0.2 and tau equal to 1000. So we have the one pulse solution, which is always stable as we saw before. We have two non-equidistant pulses, 4 non-equidistant pulses. Interestingly here, the 5 equidistant pulses solution coexists with the 5 non-equidistant pulses solution. And we have also solutions corresponding to 6 and 7 equidistant pulses in the feedback loop. So here we represent in the tau kappa plane the regions where the different solutions exist. So here for the one pulse solution, here for the 2 equidistant and 2 non-equidistant pulses solution. So we see that the 2 equidistant pulses solution exist for the smaller values of tau, and it gets unstable and gets replaced, let's say, by the 2 non-equidistant pulses solution as tau increases. And for the other solutions, we have regions where the two coexist. So overall, what we see is that the solutions with equidistant pulses tend to exist for the smaller values of tau. When we increase the value of the feedback delay, they always get unstable at some point. Here, this happens later for the 4 pulses solution, then again later for the 5 pulses solution, for the 6 pulses solution. For the 7 and 8, we don't even see it here for this range of tau, but this happens for larger values of tau. And at the same time, we have, when we increase tau, the emergence of these non-equidistant pulsing solutions. And similarly, when we increase the value of tau, the number of pulses, sorry, the region where both the solution with equidistant and non-equidistant pulses exist becomes larger and larger. So this is represented by the overlap here. So it is rather small for the case of 3 pulses, but it gets larger for the region of 4 pulses, and even more for the region of for the case of 5 pulses. So overall, what we see here is that the locking regions are particularly wide. We have really large regions of locking where we see the non-equidistant pulses. And also that the periodic solutions with n equidistant and n non-equidistant pulses can coexist in large regions of the parameters. This is what we see here, for example. So the next question is how do such large regions of locking emerge in the parameter space? So usually we have more small resonance tongues can correspond to rather small regions of the parameter space. And here it's quite unusual to see such large regions of locking. So this is what we investigate here in the few last slides. So we wonder what the mechanism is behind the emergence of these large locking regions. And to investigate this, we will follow the evolution of a 1,4 resonance tongue when the pump parameter A is varied. So the 1,4 resonance tongue corresponds to the region in which we have the existence of a stable periodic solution with 4 non-equidistant pulses. So here I start from a large value of A, so it is larger than the one we considered before, and we will see how from this configuration that I will discuss here, we can go to a case where we have these very large regions of locking. So here we have a bifurcation diagram in the tau kappa plane of feedback parameters. And so we have different bifurcation curves. So the blue curve is a Hopf bifurcation curve, where when we cross this curve, some periodic solutions can appear. And so the emerging periodic solution is stable when the line here is thick, and it's unstable for the thin parts of these Hopf bifurcation curves. So what we see is that when the delay becomes quite large, this Hopf bifurcation curve starts to self-intersect in Hopf bifurcation points. And at these Hopf bifurcation points, we have the emergence of torus bifurcation curves, which are represented here in green. And at these torus bifurcation curves, we can have the destabilization or stabilization of a periodic solution, and we can have the emergence of stable or unstable torus, so which can lead to, for example, quasi-periodic dynamics. And so we zoom here on around some of these torus bifurcation curves, which are represented in green. So here is a zoom of this bifurcation diagram in the framed area here. And so what we see is that we have 2 pairs of torus bifurcation curves emerging from Hopf bifurcation points. And along these torus bifurcation curves, we have resonance points where the rotation number is 1,4, for example, here, or 313. So we have a rational ratio of this rotation number. And so from these resonance points, we can have the emergence of resonance tongues, so that small regions of the parameter space bounded by curves of saddle node bifurcations, represented here in pink. And inside these small regions, so for example, here in between the 2 curves of saddle node bifurcations. And here we have two as well, but we don't see them because they are very close to each other. But in between these two curves, we can have locked dynamics, so which here corresponds, as we saw before, to non-equidistant pulses. But here, there are very small regions of the parameter space. And so now what happens when we decrease this value of A to go towards the value we considered previously? So when we decrease A here quite drastically, if we zoom around one of these regions, so for example, this pair of torus bifurcation, we see that we still have very small regions of locking. Here we have always two curves of saddle node bifurcation, and in between both, but we don't even see the region here, we can have stable non-equidistant pulsing patterns. But more interestingly, here we have these particular resonance tongue, the 1,4 resonance tongues, which starts to enlarge a little bit, to grow a little bit. And so for this value of A already, we have a region of the parameter space in tau kappa, where we can see when we can practically observe these locked dynamics, because the region is a bit larger. So we focus on this particular resonance tongue here. When we decrease A further and we go back to a larger view of the bifurcation diagram, this resonance tongue here became this one. So it's still reasonably large, but not as massive as we saw before. But in the meantime, as we decreased the value of A, we had a massive locking region which arrived from the very large values of tau. So it comes from infinite values of tau, and as we decrease the value of A, this moves towards smaller and smaller values of A. And here, this gets very close to the original resonance tongue that we see here. And when we decrease A a little bit further, so here it's very sensitive in A, these two regions merge through a saddle transition to form a very large here region of locking. So this is how we get these massive regions of locking, in which we can see locked periodic solutions corresponding to non-equidistant pulsing patterns. And when we decrease A further, we see that here we have another 1,4 resonance tongue, which comes from another 1,4 resonance point along another torus bifurcation curve. And when we decrease A, this gets closer and closer. These two 1,4 resonance points come closer from each other. And finally, we undergo another saddle transition, which means that now this whole region of locking is only one. It's not represented here, but when we decrease A further, this small island here shrinks and collapses on itself. And so it finally disappears through a minimax transition, which means that we go back to a massive region of locking, which corresponds to the region of stability of 4 non-equidistant pulses that we saw here. So finally, what we see here is that in this system, originally small resonance tongue coming from a 1,4 resonance point undergoes different saddle transitions and transformations and result in very large locking region, which means that we can practically observe the locked periodic solutions. And as a conclusion, what we can retain from this talk and from these results is that we studied an excitable system with delayed feedback. So we studied it in the form of an optical system, of a microlaser subject to feedback, but it's quite general. In particular, the model is quite generic, and excitability plus delayed feedback beyond the case of regular regenerative pulsing solutions can lead to a high degree of multistability. In particular, we have the coexistence of stable pulsing solutions with both equidistant and non-equidistant pulses in the feedback cavity, depending on the time scales ratio. So this really what drives the dynamics here, and let's say says if we can or not observe non-equidistant pulsing patterns. So importantly, because of the particular features of the excitable system, we have a difference between short-term and long-term dynamics. So in the short term, almost any pulsing pattern could be sustained for hundreds of round trips, but this doesn't mean that this corresponds to a stable solution. And we really have to study the long-term dynamics, in particular through bifurcation analysis. And here we see that we always have a convergence towards one of the slowly attracting periodic solutions. And these correspond to different kind of pulsing patterns. And interestingly, we can have the emergence of very large locking regions, which correspond to pulsing patterns with n non-equidistant pulses, and these emerge from 1n resonance tongues. And their range of existence in the space of feedback parameters, so feedback delay and feedback strength, depend very sensitively on the pump parameter. And this is of interest because the pump parameter is the main control parameter in an actual experiment. So thank you very much for your attention. And if you have questions, or if you want some clarification, I'm really happy to answer.
Okay, thank you, Soizic. So for questions, like feel free to unmute yourself and ask questions, or you can also put it in chat and I will read it out. Yes, I'll start with one question that I've been thinking about. So the boundaries between different regions, I think particularly towards the end, yes, here. So these are, you calculate them like using continuation basically as resonance tongues. Did I understand correctly?
Yes, so well.
So these are not like basins that you calculated from direct numerical simulations.
Well, actually, at first, it's what we did because at first we didn't understand that it was boundaries of resonance tongues. Simply because what is quite interesting is that when you end up with this configuration where you don't have any connection to a resonance point anymore, and that was quite intriguing to us because, okay, you have this massive region of locking, but it doesn't connect to any actual resonance point. So at first, we actually computed it in simulation, and then when we understood that it was boundaries between resonance tongues, yes, then we picked up a first point in simulation. For example, a solution like this, and we know that it's stable because we let the simulation run for a very long time. And then indeed we compute it as boundaries between resonance tongues.
I had a curiosity about the simulations. So in terms of numerical methods, like what did you use, and was it like how careful one should be with running this kind of simulations? What was it tricky to pick the numerical methods?
It's not necessarily tricky for simulation, but yes, you have to be careful about a few points when you deal with delay systems. But I mean, there's dedicated numerical methods for that, which are available in MATLAB or Python. But what you have to be careful about is the ratio between your time delay and your time step, because you know, if, for example, you didn't calculate your solution at t-2, because, for example, your time step is not a submultiple of your delay time tau, then your algorithm will use an approximation, and then you can have really ongoing errors, you know, and it can really be tricky in that case. But apart from that, you have to take care about that for when you simulate delay systems. For time domain simulation, it's not that tricky otherwise. For continuation and bifurcation analysis, then you have to use dedicated methods, and in particular the DDE Bifurcation package in MATLAB, which is really dedicated to DDEs. In that case, you really have to use dedicated methods for delay equations.
Yeah, I actually have a curiosity. Is there any connection here with delay eigenvalue problems It's something I stumbled upon some time ago, kind of generalized eigenvalue problems that involve polynomials, of matrices instead of just the linear type of eigenvalue problem. I was wondering, and I've seen them used in when modeling nuclear reactors or tumor growth with delay equations. I was wondering if they play any role here, or
I don't know. I mean, I'm not really a specialist of that, but indeed, stability for delay equation is a bit tricky. I don't know if it's if it's related to what.
Yeah, that was exactly stability. Yeah.
Yes, it's tricky because then what's tricky with delay equations is that your phase space becomes of infinite dimensions. So we have only 3 equations here in the model, for example, GQI, so it can seem rather simple. But the point is that from the moment you introduce a delay time, to define, for example, your simulation, you cannot define only your initial condition for GQI, and so you don't have only 3 initial conditions. You have to define an history of initial conditions. So you have to define the history of all your variables on the whole minus tau, negative tau, 0 time range, So from that point, you switch to an infinite dimensional dynamical system. And so you have infinitely many eigenvalues or here Floquet multipliers for your periodic solutions. So yes, I mean, calculating stability is much more tricky than for ODEs, for example. Yeah. And yes, you have an infinitely many. So the good point is that here for let's say this kind of delay differential equations, they accumulate towards 0. So okay, you only have a few of them which are outside, for example, of your unit circle here, but it's indeed a more complicated problem than for ODEs. Then you have dedicated numerical methods again, but tricky things can happen indeed with the Floquet spectrum here. And actually, for actually the same system, I think that Stefan Herschel published a paper on or maybe Jan Sieber on pulsing systems published some paper on the structure of the Floquet multipliers and how you can deduce some derive some features of your Floquet spectrum. But it's a tricky point, especially when your delay becomes large. And actually here we are with this value of the delay we consider here, we are kind of on the edge of the ability of the stability computation in DDB for this system. Then we have to employ other methods more involved.
Okay, thank you.
Thanks. Thanks a lot.